Good morning, all you physics students, or I guess maybe afternoon for many of you. We are broadcasting from my house. I'm isolated, I'm quarantined, but I've been washing my hands like crazy. Oh, also, I got an owie, a little owie. Okay, we're going to start with chapter 18. This is the first part of it, and we're going to learn about refraction, refresher, and then Snell's law, which is what's going to be the governing equation for us. If you recall, refraction happens when light is transmitted from one media to another. When that happens, speed changes. When speed changes, the light ray also changes direction. And if you recall, we talked about it in terms of a Segway scooter. So we've got a boundary right here, and let's say we're air at the top, water in the bottom. Air is a fast media, so we're going from fast to slow. And if you recall, the light ray has to bend from fast to slow towards the normal. Fat science teacher. So, the first thing we do is we draw the normal to the boundary. That's at 90 degrees. We'll have a ray coming in. Pick any angle. This is the incident side because that's where the light ray starts. Down here is the refracted ray. So that's where it goes. So, ray coming in, if you recall, we said think of it as a Segway scooter because this wavefront has a leading edge and a trailing edge. Just like that, when the Segway scooter's first wheel, this leading wheel, hits the boundary, it will slow up compared to the part of the scooter that's still in the fast media, that part of the wave. And so this wave edge will travel much further than this wave edge. So we'll end up changing the direction of the wave. And you'll get a refracted wave that looks like that. The angle of refraction is given here. And recall the angle of incidence is the same from the ray to the normal. That's how you would measure it. Same thing down here. So in this case, fast, slow, towards the normal, theta I must be greater than theta R. Okay, let's flip it now, and let's go from the slow to the fast. Now we're going to go from water to air, and if you recall, slow, fast has to bend away from the normal. And again, we'll draw our ray coming in. We have an angle of incidence, and the Segway scooter analogy still holds, so the leading edge of the wave hits the fast boundary before the trailing edge. It goes much further than this trailing wheel. If you're on a Segway scooter, think of a wave, and therefore it again will change directions. When it hits the new media, all of it, it will travel at the same speed, and so it's changed directions. And now here we've got theta R, and theta R will be much bigger than theta I. So fast, slow towards, slow, fast away. Okay, now, of course, this has been mathematically modeled, and a guy named Snell, who's a German physicist, did this. And what he found was the ratio of the sine of the incident angle divided by the sine of the refracted angle is a constant for any two given media. And this constant depends upon something called the index of refraction. And that index of refraction is characteristic of whatever medium the wave is traveling in. There's a table on page 493 which you will need to use to solve the homework problems. The only one you really need to remember is the index of refraction for air, which is 1.0003. It's actually 1.000 for a vacuum. So what Snell figured out experimentally or empirically was that the index of refraction on the incident side media times the sine of the angle of incidence always equals the index of refraction on the refracted side times the sine of the refraction angle. So this then leads us to what does n really measure? Well, actually, it's really a function of how fast light travels in a substance S compared to how fast it travels in a vacuum. So the definition of this index of refraction is n sub s for any substance is c divided by the speed of light in that substance. So what you can see from this is that the index of refraction always has to be greater than 1 because light never travels faster than it does in a vacuum, which is 3.00 times 10 to the 8th meters per second. Okay, let's do a sample problem. This is problem 47 on page 514. And in this problem, we've got air and a liquid. We don't know what the liquid is. Our job is to figure out what the liquid is. So we've got a light ray coming in. Here's our boundary. Air on the top, liquid on the bottom. I've drawn in my normal, which is at 90 degrees. And we've got an angle of incidence we're told is 30 degrees. So theta I is 30 degrees. The wave hits the boundary and it changes direction so that the angle of refraction is 22 degrees. If this was a laser, you would see this ray change directions. And you're going to do a little analysis as one of your assignments for next time. So we use Snell's law. N sub I sine theta I equals N sub R sine theta R. Our job is to find theta R. So we'll rearrange the equation. Take N sub I divided by N sub R, move that to the other side, times sine theta I. This is an I. And then theta R is equal to the arc sine. You got to take the arc sine of N sub I over N sub R sine theta I. Okay, recall, quick little math lesson. If the sine of an angle is equal to n, to find the angle, you take the arc sine, inverse sine of n. Make sure you know how to use your calculators to find that. You will be doing that a lot. Okay, so let's plug in our numbers. Arc sine n sub I is 1. Remember, it's air. We're told that the oh my goodness, stop in the name of love. We don't want theta R, we want n sub R, right? Okay, so let's resolve that. And we'll find n sub R equals n sub I sine theta I over sine theta R. So n sub I is 1, sine 30 over sine 22, and you solve that, and you find n sub R is equal to 1.33. Funny how you can screw things up when you know the answer. We look in our table and we say, whoa, what has an index of 1.33? Agua! And again, I can find that on 493. So again, we are looking at water as the liquid. Yeehaw! I'm upside down. See you next time.